That's one. And this is another. Again, using the wedge and dot bonds. And I think you'll agree there's no way we can turn one of them into the other just by manipulating the molecule. These two are different compounds. So these two are stereoisomers. Because there's no way you can just turn around a single bond or something like that without breaking bonds, which is not allowed, and turn one molecule into the other. So these two are different. I could, by the way, have drawn this with both bonds being dotted bonds. That then will be the same molecule. All you've done is turned the molecule over. So those two are the same. But we need different names for those two molecules since they're different compounds. And so this one we call cis-1,2 dimethyl cyclobutane. And this one over here we call trans-1,2 dimethyl cyclobutane. These names do get long, I will certainly admit that. So we need different names. So basically the definition of cis is either both bonds up or both bonds down. And the definition of trans is one bond up, one bond down. And so again, the reason we need to make the distinction is because those two molecules are different. They're different compounds. They have different properties, slightly different reactivities. And so since they're different, they need different names. This is not like an ethane. Both staggered and eclipsed ethane are still both ethane. They're the same molecule. All we've done is rotated around that carbon-carbon bond. But those two now legit are different molecules. And so we need different names for them. And so this is how we do it with disubstituted cycloalkanes. You could imagine doing the same thing with substituted cyclopropanes, cyclopentanes, etc. But that's how you deal with it. And I think you're only going to run into situations where there's just two substituents like that. So that's how you distinguish them. One will be cis and one will be trans. Maybe we'll do another example. One more example won't do anyone any harm. Maybe we'll go crazy and make one bromine and one chlorine. So here I think we should number with alphabetical priority. Bromine comes before chlorine. I think that's slightly better. So I think I'm going to call that carbon 1, that carbon 2, and that carbon 3. Otherwise, they would be 1, 2, 3, 4. That's too far apart. You want the sum of the numbers to be as small as possible. So I think the best name for this guy would be trans 1 bromo, 3 chloro. I'm losing my mind here. Cyclopropane, a pentane, cyclopentane. Don't forget the cyclo if it's a ring. I think that's the best name. I don't think one could do any better than that. Good, so that's basically how you deal with it. Now, there is another issue on top of this, which is technically there's two different trans compounds, because you see, going back to the dimethyl cyclobutane, you see how the top one is up and the bottom one is down. We could also have made the top one down and the bottom one up. And in a couple of chapters, we're going to learn those two compounds are called enantiomers. So I don't think we need to worry about that yet. I don't think that's an issue we need to worry about yet. But again, notice that there's only one cis stereoisomer, because if you draw both of the methyls with dotted bonds, it's the same thing. You've just turned the molecule over. But technically, there are two different trans stereoisomers. Those are called enantiomers. But either way, and again, I don't think we really need to worry about that just yet. But these two, the cis and trans compounds, are not the same molecule. They are stereoisomers of one another. I mentioned this because I noticed an OWL question that asks you to draw a stereoisomer of a different one. And so it'll give you some molecule. And it's then not asking you to draw that molecule, it's asking you to draw a stereoisomer of that molecule. And I think you'll find they're talking about one of these cis-trans distinctions. That's what they're getting at. So we do those problems ourselves, and it's tempting to yell at students for not reading the directions, but I got to tell you, it's happened to me too. And I will get it wrong. I'll go, oh crap, I didn't read the directions. So I understand how that goes, and I'm in no position to yell at you guys about that. Good, so I think that's about all we need to say about that. That leaves me 20 minutes for cyclohexane, and I hope and pray that will be enough. We'll get done what we can. Well, actually, what have I done? Oh, I see. So cyclohexane has some intriguing properties in terms of its conformations. I just want to make all of the so-called equatorial hydrogens the same color and all of the so-called axial hydrogens the same color. One more I need to switch. So hopefully you read about those terms. Those aren't completely new terms to you, but we'll go over that today. We should have time. Good, so there's our cyclohexane. So certainly when you're just drawing a flat structure, it's absolutely not wrong to draw cyclohexane like that. But you do need to bear in mind cyclohexane is not a perfect hexagon. Benzene is, cyclohexane is not. But cyclohexane is puckered in three-dimensional space, as I'm trying to get it to sit on. Did it work? Sort of? Maybe? It's not really behaving itself, is it? Oh, that's not so bad. Yes, I can live with that. That's good. So as you can see, cyclohexane has a three-dimensional shape to it. And there are certain conventions we follow for drawing that shape. We call that's the lowest energy conformation of cyclohexane. And we call that the chair conformation. There are other conformations, but this is the lowest energy conformation. And the reason we call it the chair conformation is from any given angle, you can imagine lying down in the chair over here, and your butt goes in here, and your head will go over here, and then your feet are dangling over here on that end. Looks like one of those loungers that you'll find at like the swimming pool or something like that. So, and again, I don't want this to be at all intimidating. I have a significant advantage over you guys. I've been drawing these things for like 25 years. So I understand drawing these things takes some getting used to. But cyclohexane C6H12, I'm just going to draw it in its chair conformation. That looks a little bit ugly, but I guess I can live with it. I've done better. So there we are. Those are the 12 hydrogens on cyclohexane. And in your book, they kind of make it look a little cooler by bolding some of these bonds to make it look like they are in front. That looks kind of cool. You can do that if you want. I consider it optional. But that's the basic shape, just so long as you understand that there's a carbon-carbon bond back here that's behind this hydrogen. So you have to kind of think in three dimensions in order to understand that fully. So that's one of the two chair conformations. And as you can see, all 12 hydrogens are not created equal. There are 6 hydrogens that are sticking either straight up or straight down. They're white at the moment, and we call those axial hydrogens or axial positions. So we'll define axial as straight up or straight down. And in unsubstituted cyclohexane, you will find 6 axial hydrogens, 3 of them pointing straight up, 3 of them pointing straight down. The other 6 positions are called equatorial because they are literally sticking out from the equator. They're sticking around the center of the molecule. So positioned around the center of the molecule, positioned around, around the periphery of the molecule, let's say. Periphery of the molecule. And so there's 12 of those as well. Sorry, 6 of those as well. And you can see them. They're the ones in green at the moment. So those 6 positions we call equatorial positions. Still, the rules for cis and trans apply. If you've got a disubstituted cyclohexane, and then that means that either both are sticking up or both are sticking down. If it's trans disubstituted, then one's up and one's down. And I will just say it's a little easier to tell up and down on the axial positions. See, those 3 hydrogens are definitely pointing up. Let me get it actually on the camera. There's like no question about that. These 3 hydrogens equally definitely pointing down. It's very easy to tell. The equatorial ones are a little more subtle. So this equatorial position is pointing down. And the way you can tell is that the axial position in the same carbon is pointing up. So this one must be down. And I think you can see it's pointing down a little bit. I've tried to reflect that on my drawing over there. Again, I did the best I could to show 109.5 degree bond angles. So here, that one's sticking up just a little bit. You can tell the axial position is straight down, so this guy must be up. So that's how you do it. And if you have to deal with cis and trans, it's the same as before. Cis means both up or both down, and trans means one up, one down. So, right, and we'll get to cis and trans alkenes in a little while. But that wasn't exactly what I wanted to do. Let me see if I can manage something over here. Whoops, that wasn't what I was trying to do. This will be really cool if I can. That's not what I wanted to do. I'm trying to move it, and there is a way of doing that. There we go. Yay. So that's one of the chair conformations. And in terms of conformations of cyclohexane, there are 2. They're both chair conformations. And in the case of just unsubstituted C6H12, they're of the same energy. So in order to get from one to the other, if you have access to a molecular modeling kit as you're practicing, this would not be wasted time. But in order to change from one to the other, you kind of grab them by opposite carbons and pull up on one and down on the other. And it's going to look like I just performed a magic trick, but I'm going to let you guys admire the results. We'll talk about that magic trick in just a moment. But the other conformation, which again is equivalent in energy, it's really not the best cyclohexane I've ever drawn. Something like this. I'm going to put the bonds in first and then the H's. So there's all the bonds. We'll put in our 12 H's. And last but not least, there we go. So those are the 2 equivalent in energy chair conformations. And really, in between this, if we wanted to be completely correct, we draw an equilibrium arrow. So please note, this is not a resonance situation. I did not draw a resonance arrow. I drew an equilibrium arrow. These really do flip back and forth. They're distinct species. And those 2 chair conformations are in equilibrium with one another at room temperature. And as you can imagine, since they're of the same energy, another way of saying that they're the same energy is to say that the equilibrium constant is 1, right? There's a 1-to-1 ratio of one to the other. So there's no particular favoring of one of those chair conformations over the other. And that ring flip interconversion, as it's called, is pretty rapid at room temperature in a sample of cyclohexane. Now getting back to the magic trick. Anyone notice what happened when I did the ring flip conformational change to the axial and equatorial positions? What happened to the green and the red balls? Well, that's actually a good point. One thing I didn't mention. One thing about cyclohexane is all of the positions are perfectly staggered. So there's no ring string. But I wouldn't say that they interconverted, didn't they? See how the green ones are equatorial now, and then you do the ring flip. Now suddenly they're axial. Now they're pointing straight up or straight down. So of course that wasn't a magic trick. That really does happen in the ring flip conformational change of cyclohexane. So, but as long as all 12 of the attachments are to hydrogen, those two are of the same energy. And I have 9 minutes, and I think I'd like to cover just one more aspect of cyclohexane, which is, and I didn't bring any, I should have brought at least one more carbon. Oh well. What if it's not C6H12? Let's say we replaced one of those hydrogens with any other group that you like, let's say a methyl group. Yeah, I can do better than that. Or maybe not. Let's say that we put a methyl group over here. So we've got methyl cyclohexane. No cis or trans distinction because it's just got the one substituent group. So there's methyl cyclohexane. If you were going to draw this as a flat structure, you'd just stick a CH3 on. Wherever you like, since all 6 of those positions are the same. Then we also don't need to worry about wedges and dots, since whether you draw it with a wedge bond or a dot bond, it's the same thing. You just flip the molecule over. So that's one way. This is now going to be in equilibrium with another chair form. In which the methyl group switches from equatorial to axial. So here our methyl is equatorial. On this one, it will be axial. And as a matter of fact, it will wind up down here. I don't really want us to get lost in the weeds about all that. But it does wind up down there. Like that. So as a matter of fact, when you do the ring flip, it kind of appears, because we're pulling this part down and we're pushing that part up, it kind of appears like everything moves clockwise. It doesn't actually, but it looks like it does. So that's how this methyl group winds up over there. Here our methyl group is axial. So that's a function of what we just saw a moment ago. You saw how my axial and equatorial positions have been converted. So the same thing will happen here. For one of those for one of those conformations, there, they almost got me. For one of those conformations, the methyl group will be equatorial, and for one of them, the methyl group will be axial. And as it turns out, the one that has that methyl group in it, I just chose methyl as an example. I could have picked any other group that you like. But the one that has the group equatorial is going to be lower in energy. And the one that has the methyl group axial is going to be higher in energy. And there's a very good reason for that. It's because this methyl group, when sticking straight down over here, is going to bump into the 2 hydrogens that are on the same side of the molecule and also axial. Axial H's on same side. What a crazy thing for me to do, to write down the thing that I've said. You know, what comes next? Next, you'll say I should be reading the book or something like that. Jeez. Anyway, enough of that type of sarcasm, I suppose, at least for now. So that's why. And that phenomenon is called torsional string. I mentioned it before. It's the phenomenon of two or more groups bumping into each other that are not directly bonded together, but are close in three-dimensional space. So that's an example of torsional strain. And that torsional strain is relieved when the methyl group is in the equatorial position. Now it's not bumping into anything. So I think that's about all I needed to say about that. I still have 4 minutes. I'm trying to think of something useful I can do with it, and I've already thought of something. Let's name another cycloalkane. I don't want to jump to a totally different subject all of a sudden, but I do want to use class time. But I think that's, I don't really want to burden you with too much more than that in terms of cyclohexane and its conformations. Just be aware that it's a conformationally mobile molecule. Certainly, even when it's unsubstituted, you have these two equivalent energy chair forms that are rapidly interconverting. Again, not resonance, not resonance. Please, please and thank you. This is not a resonance situation. This actually is two species interconverting. So that's not a resonance situation. You'll notice I drew the arrow to reflect that. That's an equilibrium arrow, not a resonance arrow. And then the idea that in cyclohexane, when it does undergo what we call a ring flip interconversion, the axial and equatorial positions interconvert. The positions that had been axial become equatorial. The ones that had been equatorial become axial. And I honestly, I can't promise that's every last little detail, but I think that's the vast majority of what, if not 100%, I think that's at least 95%. Of what you should concern yourselves about. As always, it's in the book, you have to know it, unless I specifically say you're not responsible for it. But I think that will be at least enough to get you through the main ideas. So that leaves us 3 minutes to name a cycloalkane. Let's go nuts. Let's go crazy. Let's name a cycloheptane. Come on, you want to know how to draw a 7-membered ring. I just know it. I think that will work. So we want to say that the cycloheptane has an ethyl group in one place and 2 chloros in another place. And we would want to do that preferably in such a way so that the sum of all the numbers is as low as possible. And I believe we'll accomplish that if we call that carbon 1, this one carbon 2, and this one carbon 3. Then we'll want to name the chloros first, since C comes before E, so chloro before ethyl. And so I might have made that a little too easy, but I think that one should be called 1,1-dichloro, 3-ethyl. This is actually all one word, cycloheptane. I think that's the best name, because that way we wind up with the smallest possible sum when we add up all of those numbers together. So I'm glad we at least got to do one example with the cycloalkane. But with that, I'm actually pretty much out of time. So have a great day. Stay dry. I don't know if it's going to rain or not, but I will see you all on Friday.